Kepler's laws are three laws developed by Johann Kepler in the early 1600s that describe planetary motion. At this time, there was no telescope, and the only planets known were Mercury through Saturn, six of them. Kepler had very precise data about the positions and motions of the planets that had been collected by Tycho Brahe before he died. And he put together these three empirical laws. And what that means, they fit the data. Kind of like if you asked Excel or some other computer program to do a curve fit, it can come up with an equation that best describes your data, but it doesn't give you any physical insight into where it comes from. And these three laws are: planets move in orbits which are ellipses with the sun at one focus. Number two, the line joining a planet and the sun sweeps out equal areas in equal times. And number three, p squared equals a cubed, where p is the planet's orbital period in years, and a is the semi-major axis, which is sort of like the radius of the planet's orbit measured in astronomical units. One astronomical unit is defined as the distance from the Earth to the Sun, and we now know this is about 150 million kilometers, but this wasn't figured out until the 1800s. They just had an idea of the relative distances of the planets, but not the absolute distances. Newton came along and was able to explain the physical basis for Kepler's laws, and we're going to see if we can do the same. Before Kepler, the way people thought the solar system was set up, but they also confused the solar system with the entire universe. The Earth was at the center, and the planets and the sun and everything else moved around the Earth in circular orbits. They had to be perfect circles. Close observation of the planets showed that the planets sometimes go one way through the sky, and then for a little while, for days or weeks, they'll go backwards through the sky relative to the stars, and then they'll return to the right direction. This is called retrograde motion, and if you want to explain this with circles, you have to have circles going around orbits which are also circles, kind of like an arrangement of gears. And as the observations got better, these models of circular orbits, epicycles and deferents, got more and more complicated. If we wanted to define a circle, what we could say is it's the set of all points that are a particular distance r from one special point, which is the center. For an ellipse, we have two special points, which we call the foci. Focus is one of them. And the ellipse is a set of all points for which the distance from a point to one focus plus the distance from that point to another focus is a constant. The value of this constant we call 2a. So in other words, in this picture here on the right with the ellipse, x plus y is equal to a constant, and it's 2a. And if you move around the ellipse, that same constant, x plus y, is that same constant for any of these points. The foci are red dots here on the right, and they both lie on the longest symmetric line through the ellipse, and that's known as the major axis. The length of the major axis is 2a, and you can see, if you imagine we're looking at this point here, we'd have this distance and then that distance, and we could move this over here, so 2a does have to be the length that we get when we add x and y for all the points. There's no common name for the distance between the foci, but we usually represent it as 2 times c. And then we can talk about the eccentricity e of the ellipse, and that's how far it is from a circle. It's the distance between the foci divided by the major axis, or c divided by a if we cancel the 2's. If we had a circle, these two foci would move together and be 1 point, and c equals 0, a is the radius, eccentricity is 0. If we have a very long flattened ellipse, and Halley's Comet's orbit is a good example, the foci are very close to the ends, and at the eccentricity is close to 1. In the case of Halley's Comet, it's 0.967. If you want to see what this looks like, these are not to scale, but they are the right shape. The green orbit here, this represents Earth's. It looks like a perfect circle. Earth's eccentricity, the orbit of Earth's eccentricity is very small. It's 0.0167. Pluto, which if you look at the sort of original 9 planets, this had the most eccentric orbit. It was about 0.25. It still looks an awful lot like a circle. If you don't measure it carefully, you probably wouldn't notice the difference. Halley's Comet, which is this fairly eccentric orbit, here this is obviously not a circle anymore. To prove this, to prove that the orbits of the planets are ellipses with the sun at one focus, takes a little bit more involved math than we typically use intro physics. If you take a junior level mechanics course, what you'll see is whenever you have a force that depends on distance as 1 over r squared, and it's attractive, you'll get orbits that are what are known as conic sections. That is, slices through a cone. That includes ellipses, circles, parabola, and hyperbola. The second law is a little bit easier to prove. If we imagine a line connecting the sun and a planet, the area it sweeps out in a time delta t is an arc. If both times in this picture are delta t, the area of the green triangle has to be the same as the area of the pink triangle. The pink triangle is short and fat, the green one is long and thin, so what that means is we've got a long distance to cover around the orbit for the pink triangle, and a much shorter distance around the orbit for the green triangle. The planet will speed up when it's close to the sun and slow down when it's far away from the sun. How can we prove this? How is Newton able to prove it? If we take the limit where delta t goes to 0, these two shapes become exact triangles rather than segments of a circle or an ellipse. The area of the triangle is 1/2 base times height. If we call the height of the pink triangle r pink and the height of the green triangle r green, these are the distances from the planet to the sun at these two times. The base is then going to be this distance here. That's going to be r times theta, where theta is this opening angle of each triangle. So for the base, we could say it's r pink times theta pink or r green times theta green. That would tell us the area of the pink triangle, for example, is 1/2 r pink squared times theta pink. And instead of theta, we could write this in terms of angular velocity omega. So now the areas are 1/2 r pink squared omega pink delta t, because that is theta, and the same thing for green. Kepler's second law says these two are equal if the delta t's are the same. So we write that like this. We simplify it. We get rid of the 1/2 and the delta t, since the delta t's are supposed to be the same. We get this form. And finally, we can multiply by anything we want to as long as we do it on both sides, so we multiply by the planet's mass. When we do this, what you notice is on the left we have angular momentum of the planet considered to be a point mass where it's in the pink region, and on the right, angular momentum where the planet's in the green region. This is the reason Kepler's second law works. It uses conservation of angular momentum. If there are no external torques, this quantity has to be the same everywhere in the orbit, and that's what makes the equal areas and equal time law work. Finally, for the third law, we can go back to the expression we found when we're looking at centripetal acceleration caused by gravity. When we have two things in orbit, we use the reduced mass, and we found this. We can expand the reduced mass out to this, and we get back to this expression we had some time ago. Now, we can also use the fact that velocity in a circular orbit is 2 pi r, the radius, divided by the period, p. This is just distance divided by time. If we make that substitution, we can rewrite this way. And we can further rewrite it like that. G times the sum of the masses divided by 4 pi squared is r cubed over p squared. Now, of course, Kepler didn't have this, but if we have AUs for r, and years for the period, the units on the left will just be solar masses. So we'd have m1 plus m2 equals r cubed over p squared. This is not quite what Kepler's third law is, but we're getting there. The important thing here is we're adding the sun's mass to the mass of one of the planets, and even with Jupiter, Jupiter's mass is about 1/1000th of the sun's. So if Kepler had had incredibly good data rather than just pretty good data, he might have seen that r cubed is not exactly equal to p squared for all the planets. It's just really close. However, when you look at the size of these discrepancies, it's pretty easy to see that this is going to look very much like 1 to just about anybody's ability to measure, and that gives us r cubed equals p squared. If this only worked for the planets, it would be interesting and nothing else. The thing that's very useful about it, it works for any two masses in orbit. This is how we find the masses of stars far away from Earth, where we will quite possibly never be able to send probes. Just about every bright star in the sky is really a binary system of a couple of stars that are very close together compared to their distance to us, and therefore look like a single star. If we observe them with a telescope, we can look at things called redshift and blue shift and figure out the total mass of the system by watching how long it takes them to make an orbit and how large that orbit is. This is also where we get the figures for masses of the planets, mass of the Earth itself. If we have planets without moons, like Venus and Mercury, the estimates before the space age were not great. It was just assumed that they were about the same density as the Earth, and that's how we figured out the mass. But once a satellite was able to be put into orbit around Venus and around Mercury, we were able to look at the distance between the satellite and the center of the planet and the time it takes the satellite to go around and figure out the planet's